Here's an example of what's known as an apportionment problem. Mom has a total of 50 pieces of candy. She's planning to divide them among her 5 children. She's going to use this as an opportunity to teach her children about the relationship between work and reward. So she announces that the candy is going to be divided among them at the end of the week in proportion to the amount of time each of them has spent on chores that week. So you do more chores, you get more candy. Right? If you worked twice as long as your brother, you're going to get twice as much candy as your brother gets. So here are the numbers at the end of the week. Each child meticulously recorded every single minute of chores that they did. And I want you to take some time in your groups, find a solution. How much candy should each child be given of the total of the 50 pieces of candy? How many pieces should each kid get? Assume that you can't break the candy into pieces. Okay, it's not candy that you can break up. Okay, so I've seen several different methods being used to calculate this. So probably the most popular one that I saw was to do this by percentages. So for each kid, figure out what percentage of the work they did and give them that percentage of the candy. So let's say Alan worked, he did 150 out of 900 minutes, right? Which is 0.16. Right? Right, or 16.67%. So Alan did 16.67% of the work. We should give him 16.67% of the candy. Okay, so he gets 0.1667 of 50 pieces of candy. Take 16.67. So that's like 8.3 pieces of candy. Okay. So he did about 17% of the work. He should get about 17% of the candy. Yes. Yes. Yeah, there are lots of different methods. I'm going to go through each one. Okay. So this is the percentage method, very popular among you. So another way that I saw was to use a proportion. So Betty, for instance, we do a proportion part to whole equals part to whole. So Betty did 78 of 900 minutes. And that means, okay, so this is part of work to the whole amount of work. What part of the candy should she get if the whole of the candy is 50? So then you can set up this proportion. Part to whole for minutes worked should equal part to whole for candy earned. So then to solve a proportion like this, remember you cross multiply. So you do 78 times 50 equals 900 times x. So 3,900 equals 900x. Divide both sides by 900. So we get x equals 4.33. So Betty should get 4.33 pieces of candy. That's her exact fair share, right? We're not splitting the candy, so we're going to decide how to round them after we figure out. We'll figure out what everyone's exact fair share is and then deal with how to handle the pieces. Yeah. Okay, so that was another method, proportion. So method 1, percentages. Method 2, proportion. Method 3, yeah, to figure out how many minutes you have to work to get one piece of candy, right? So if you take 900 minutes 900 minutes divided by 50 pieces of candy. 900 divided by 50 would be 18 minutes per candy, right? So for every 18 minutes you work, you should get one piece of candy. 18 minutes equals one piece of candy. So then you can take each child's minutes worked and figure out how many sets of 18 are in it. How do you figure out how many sets of 18 there are in a number? Divide. So the last three I can use this method for. Right? I'll just divide each number of minutes by 18. That's the number of pieces of candy they get. So let's see. Connie, we have 173. 173 divided by 18. Because for every 18 minutes, you get one piece of candy. 9.6. Okay. And then Doug and Ellie, 204 and 295. $204 divided by 18 and 295 divided by 18. And what do those come out to? 0.3, 16.4. All right, so I also heard several ideas about how to deal with the pieces, right? You can't give out 16.4 pieces of candy because we can't break the candy. You could give out 16 or 17, but you can't give out 16.4. So what are some ideas that we could do here? Good idea. Okay, so we could round everybody down. So give everyone the lesser amount, round everything down. So Betty would get 4 pieces of candy. And what's his name? Alan gets 8. Connie gets 9. Doug gets 11, and Ellie gets 16. So we're just going to round everybody down. If you deserve a fractional piece, we just say no. You just get the lower amount. Okay. But if I do that, right? If I round everybody down, I'm going to have 8 plus 4, 8 plus 4 plus 9 plus 11 plus 16. That only adds up to 48 pieces of candy. So I have 2 left over, right? So one idea is that I could give them to whoever is the closest to having a whole nother piece of candy, right? So who would be the closest to deserving a whole nother piece of candy? Connie is the closest because 0.6 is the largest decimal piece. So we could give another piece to Connie, and then we still have one more piece. Who should we give it to? Ellie. Yeah, Ellie has the next largest fractional piece. 0.4 is the next largest decimal piece.
But then why not just round up? Because that would take care of one piece of candy that we're trying to.
Yep. So I could. That's another way to do it. You could try to round using typical rounding rules. In this particular case, I would still have one piece of candy left over, and I'd have to decide where it should go. Do you have any ideas for that?
I don't.
Maybe Mom gets it. Yeah. Yeah. So that one idea is to round them all down, give the leftovers to the people with the highest decimal. One idea is to do standard rounding. The problem with standard rounding is that once you add them all up, you might get more than 50. If it turned out that all the decimal pieces were bigger than 0.5 and I rounded them all up, I'd be apportioning more than 50 pieces. But often it works, just standard rounding. We could round them all down and let Mom have all the leftover candy. Right, maybe whoever did the most could just get the extra candy. If you're the winner, that's sort of your bonus prize. That's a good way to settle it. Right. So another common place where apportionment pops up has to do with apportioning seats in a Congress, a representative government. So we have this fake small country, Parador. It has 6 states, A, B, C, D, E, and F. There are 250 seats in the Congress, which, according to the laws of Parador, are apportioned in proportion to their respective populations. Okay, so if you have more people, you should get more representation. And if you have twice as many people as another state, you should get double the representation. Okay, so I'm actually going to skip this because I think that we really figured out how to come up with the number of seats. So in this case, instead of pieces of candy, we're giving out seats in Congress. It's almost the exact same thing. So we'll skip this for now. So we can calculate the exact number of seats in each state that each state deserves, right? Or the exact number of pieces of candy that each child earned. But the problem is that you can't give out a partial seat in Congress, and you can't give out a piece of a partial piece of candy. So we just talked about several solutions. And what we're going to study in this chapter is several historical solutions, how our country solved the apportionment problem in terms of representative government. So first, some vocab. The standard quota, that is the exact number of seats each state deserves, right? Or the exact number of pieces of candy. So it can include partials, right? You might say, well, according to my population, we should get 12.4 seats in Congress. The lower quota is the standard quota rounded down. And the upper quota is the standard quota rounded up. Okay. So if the standard quota comes out as 12.4, that's the number of seats in Congress you can get. You can't give out 0.4 of a congressional seat. So we say, well, you're either going to get 12, your lower quota, or you're going to get 13, your upper quota. So the quota rule says that you should always get either your lower quota or your upper quota. If your standard quota is 12.4, you should get 12 or 13 seats. Those are really the only 2 fair options. To give you fewer than that would be really unfair, and more than that would also be really unfair. So if we have a method that gives a state too few seats, right, less than its lower quota, we call that a lower quota violation. And if we have a method that gives a state too many seats, that's more than its upper quota, we call that an upper quota violation. So if the standard quota was 12.4 and I gave a state 14 seats, what would that be? What kind of violation? Upper quota violation. They got more than their upper quota violation. All right, so the first historical solution to this problem of apportionment, first historical solution in the United States, was called Hamilton's method. So we're going to have a lot of founding fathers' names in this. So it turns out that to be a politician, back when the country was being founded, you had to also be a mathematician a little bit to be able to propose these ideas of how we were going to solve this problem. So Hamilton's method calculates each state's standard quota, gives each state its lower quota, rounds them all down, and then gives the surplus seats one at a time to the states with the largest residues. Residues are just the decimal parts. So that's exactly what you described earlier, until there are no more surplus seats. So we're going to do one together. We're going to use Hamilton's method to finish the apportionment for the Congress of Parador. So the population of each state is given, and the total population. And remember, I'm giving out 250 seats. Okay, so this was from earlier, 250 seats in the Congress of Parador. So one way you could do it is you could say, well, there's 12.5 million people in this country. So we do 12.5 million divided by 250 seats. That's 50,000 people per seat. Okay. So we do 12,500,000 people divided by 250 seats, 50,000 people per seat. So for every set of 50,000 people in the state, you get a seat in Congress. So we do each state's population divided by 50,000, and that's how many seats you get. So state A has a population of 1,646,000. Divide that by 50,000, and you get 32.92. Okay, so that's, I already have those numbers written in. So 32.92 is the exact number of seats that state A should get in Congress. If we're going to be proportionate about it, they should get 32.92 seats. You do the same thing for every state. So 6,936,000 divided by 50,000 is 138.72 seats. So those are the standard quotas, the exact number of seats that each state deserves. Then we take the lower quota. We round them all down. Doesn't matter how big the decimal part is, round it down. So this is going to be 32, 138, 3, 41, 13, and 19. So it takes some effort to break the habit of standard rounding, where to just remind yourself, round them down, right? But when I add these all up, I have 32 plus 138 plus 3 plus 13 plus 19. That's plus 41, 246. That's only 246 seats. I have 4 more seats open in Congress. So the question is, who should I give them to? Yep, we look at the decimal pieces, the residues, 0.92, 0.72, 0.08, 0.82, 0.7, 0.76. Okay. And I have 4 seats to give out, so who should I give them to? The 0.92. Yep. And 0.72, because I have 4 seats, 4 extra seats. So my final apportionment is going to be the lower quota plus another seat if you got one of the surplus. So state A had 32 plus it got a surplus, so it's going to get 33. State B had 138 as its lower quota. It got one of the surpluses, so it's 139. State C, its lower quota was 3. It did not get one of the surpluses, so it ends up with a total of 3. 41 plus a surplus is 42. 13, no surplus. 19 plus a surplus is 20. Now when I add these up, I get 250 seats. So that's my final apportionment using Hamilton's method. Questions? Does it make sense? All right, so you try one. Tasmania State has 5 different schools. The total number of students is 12,500, and we're going to apportion faculty positions based on the school's respective enrollments. So here's the school's enrollments. You might want to add a column to here called total. Use Hamilton's method to figure out how many faculty positions each school should get.